Okay, and then next problem, we have an intersection in Thomasville, Oregon, where cars turn left at the rate of L of t is equal to 60 square root of t sine square of t over 3 cars per hour over the time interval from t equals 0 to 18 hours. And the graph of y equals L of t is shown above. So for A, to the nearest whole number, find the total number of cars turning left at the intersection over the time interval. So I'm going to go to my graphing calculator and I'm going to put this function L of t in. Okay, so I have that there. One question that a lot of people have is how do you put in sine square of something? And the way that I do it, just to be safe, is I wrap the whole sine function in parentheses and then square that whole thing. So I would have parentheses sine of x over 3, parentheses sine parentheses x over 3 close parentheses squared. Alright. Now remember that this is the rate, so this is a derivative, and if I want the total number of cars turning left, I just need the integral of this function from 0 to 1800 hours. Now I'm going to assume that I'm going to need this graph at some point in the process. I could use fn_in to get this information, but I'm going to take a second to set up the graph right now. So I go to Window, and I want to have my x values go from 0 to 18, as they are there, by ones, and my y values to go from 0 to 250 by 50s. When I do that, I should be able to get a reasonable replica of that function, and I do. So what I want to do is have the integral, so that's option 7, from 0 to 18 hours, and that gives me 1657.82, so rounded to the nearest whole number would be 1658. And recall that I do have to write down in mathematical terms the expression that I'm using to get that value. And so I have integral from 0 to 18 L of t dt is equal to 1658 cars. B. Traffic engineers will consider turn restrictions when L of t is greater than 150 cars per hour. Find all values of t for which L of t is greater than 150 and compute the average value of L of t over this time interval. So I'm going to clear draw to get rid of that, and the best way to do this is to put in a function 150 and graph, and I can see there are 2 points of intersection. I'm going to do an intersect, option 5, first curve, okay, second curve, okay, and I'm just going to get a little closer to the first one, which I have. I'm going to store that value, so I'm going to go out to the main screen, and I'm going to do x store alpha a, and I've got it. I'm going to go back to my graph. I'm going to look for the second one, calc, intersect, and first curve, second curve, and guess I just need to be closer to the second intersection point than I am to the first, and I hit enter for guess. That's 16.121, etc. Quit, and I'm going to do the same thing again. I'm going to do x store, this time in alpha b, and I have it there. Now what I do want here is to find the average value of L over this time interval. So I need the integral, so option 7, lower limit is going to be alpha a, and upper limit is going to be alpha b. Now I don't just want the stuff on top, I want the whole area underneath that curve there, because that gives me the total number of cars, 736, and I need to divide that by b minus a. So I'm going to divide that by alpha b minus alpha a, close parentheses, and I get 199, again 199.426. And so I write down the information excuse me, that I needed for that problem, and it's 1 over b minus a, integral from a to b of L of t dt is 199.426, and the rates and the units are cars per hour. We'll continue in the next video.